Oh, here we are. I think Dr. Stefan is still trying to dial in. Can you hear me, though?
I can hear you.
Awesome. Oh, there's Dr. Stefan. Okay, let me capture this real quick, guys, before we start. This is always fun to try to do. Let's see. Awkward silence, I know. I think that works. Okay, we're good. Okay, let me move my face, actually. This is... and actually, Dr. Geller, you can start off by telling everybody about yourself. There's Dr. Geller, guys. You can see him on the stream. Do you have the Twitch chat loaded? Maybe?
I do? Yes, I do here. Oh, I got a network error. Let me play again.
Let me make sure that my... Give me a second. The Google audio needs to be adjusted. To that. Okay, now can you say something?
Yep.
Okay,
Hello, everybody.
There we go. There we
Can
go.
you hear me?
I think they can. I think we're
like
good.
a boss.
We're good. And there's Dr. Stefan as well, guys. You guys are familiar with him. But yeah, if you want to go ahead and tell everybody about yourself, you know, what you do in the field of astronomy, astrophysics, actually, and a little bit about what your interests are with that.
Sure. So, yeah, my name is Aaron Geller. I split my time actually between Northwestern University and the Adler Planetarium in Chicago. And I study stars, the lives of stars, and the planets that orbit them, and basically the environments that they live in and how stars interact with each other. Oh, and I can see you pulled up my website there.
Yeah, I did. Yeah, I know everybody has reference to this because there's a lot of really cool stuff on it. I was looking at some of your simulations that you do with this stuff. And I've been kind of prepping them for the differences between open clusters and globular. But seems like you studied a lot of NGC 188, right?
Yeah, so right. So all, star clusters and really mostly everything that you see in the sky is given a interesting kind of phone number name by astronomers. And some of them have more interesting names. But this one, yeah, NGC 188 is a particular star cluster that I studied quite a lot for my thesis when I did my PhD. And my collaborators and I are still studying it. I don't study it as much as I did back then. But yes, this is a group of a few thousand stars. It's near the direction of Polaris, our North Star. So it's up in the sky pretty much every night from the Northern Hemisphere, which makes it a really nice target for observations. So for my thesis, I spent many nights at telescopes observing the stars in that cluster, and then also ran some computer simulations to understand our observations a little bit better.
Awesome. So do you have those? Do you want me to run them, or do you have them? It's okay if you don't.
Oh yeah, well I do have a movie that I can show.
Yeah.
It's not actually of that particular star cluster, but it's it gets the point across well enough. So yeah, I can show it. We'll see if it will.
Do a screen share thing.
Remind myself how to share a screen on here.
Yeah. I am not very Google Hangout savvy myself, so.
Oh, you know what? I'm not.
There should be a hamburger menu up on the top right.
Says the physicist.
Yes. Well, I will. Give me 1 second. I'm going to pull it onto this desktop instead.
Oh, you're good. You're good.
Okay, so this will not be actually of that particular star cluster, but it's actually meant to show. So tell me if you're seeing something that doesn't look like my face.
Yes.
Okay, so I'm going to press play, and I'll make this full screen for you. So this is actually a movie that I developed at the Adler Planetarium that we show in our space visualization lab. And I can talk about that too. But what this is showing is, we call it the life of the Pleiades. So the Pleiades is a star cluster that's fairly close by to us, and is fairly well studied, and has stars that are all about the age of 100 million years. And what you're watching in this movie here, all those different colored points are stars. They change color, which is typically what stars do as they age, but of course we don't see that stars changing that rapidly. As you can see, there's a counter on the bottom, if you can read that, counting up in units of millions of years. So when we take a picture, when we look at the Pleiades, we think that it looks static, like all the stars are in one place. But when you look at it on time scales of millions of years, the stars move around quite a lot.
And that's actually pretty fast, right?
Yeah, well, yeah, I mean, stars, you can see how much they move actually over the course of this amount of time. You know, relative to our lifetime, they don't move very much. But relative to an astronomical timescale, they move around, they change sizes, they change colors. This is now a zoom out to a view from a galaxy scale. And those kind of purplish pink spinning lighthouse shapes are neutron stars. They are born in supernovae and they get very fast kicks that can kick them directly out of the cluster and maybe even out of our galaxy. And those green ones that you see are black holes. Those are also born in supernovae. Some of them get big kicks, although we don't really know how the kicks of those are supposed to be. And you can also see in this scene, as we're kind of zooming in, getting closer and closer to the cluster, that the stars are being kind of shredded out of the cluster by the pull of the galactic tidal field, by the gravity of the galaxy. And here we are looking deep into the cluster, zooming in on one particular gravitational dance between a group of stars. Right now, at least for me, it's lower left. Right now you see a kind of a flashing blue and red star interacting with a white star. Here comes like a yellowish beige star. Interactions like these happen all the time in these clusters. When stars come very close to each other, they can slingshot each other out of the cluster. They can even end up colliding with each other to form new stars. And this is some of what I study.
Right. So how often do stars collide? Is it a pretty common thing?
That's some of what we're trying to figure out. So in a star cluster like the Pleiades, it's not very common. You know, over the course of millions of years, you may get a few collisions. Mm-hmm. In much more dense clusters, like globular clusters, these are the largest clusters that we have in our galaxy. Collisions could be many times more frequent than you would see in the Pleiades.
So how do you even analyze, like pick out and then analyze a system?
Can you actually pause that video real quick? Because I looked at that last night, and that's actually, you're showing them moving on and off the diagram, right? Off the main sequence. Sorry, Dr. Stefan, that was actually I loved seeing that because I haven't seen that really demonstrated in any of the things I've looked at, and I liked it. It's hard to find
this transition from location to position on the HR diagram. Yeah, we can talk about that HR diagram too, if you like.
Yeah, we can after Dr. Stefan's question was a good one.
Yeah, so what were you saying, Dr. Stefan? I'm sorry, can you say it one more time?
Yeah, I'm just curious how you identify, when you have a system like that one that you're studying, how do you identify that system out of your simulation? And then how do you actually study that, I guess, conglomeration of stars within that system? Like, how do you go about characterizing its evolution? Right,
so for that particular one that you're seeing there, I literally made this visualization. It's interactive. It's not only, I rendered it to a movie, but it's an interactive where I can rotate it around and zoom in, zoom out. So I kind of looked at it for a little while and found that visually. And that's actually one of the powers of visualizing your data in this way. I mean, I get the data from the simulations as just a long text file, essentially. Here are the stars' positions, X, Y, Z in space. Here's their temperatures, their luminosities, various parameters, all as a function of time. And, I can write some computer code to go through all of those and try to identify which are the interesting, groupings. But sometimes it's easier to do something like that just by looking at it in an interactive visualization or in a movie like that. Certain kinds of stars, if you have collisions, that is flagged in the code that I use. So I get a special output file for those, and I can look at those in more detail. But different encounters like you were just watching there, it's not as easy to really draw those out. And oftentimes when I want to study those, I will just run just a few stars and watch that encounter, not with the entire rest of the cluster, and see what that encounter does on its own. That's more easy to analyze.
And so this was the simulation was the Pleiades, so Messier 45, right?
Mm-hmm. Yep.
And guys, that's the Pleiades. I even said it in chat. That's the Subaru logo.
Yeah, exactly.
A lot of people don't know that, and the guys probably thought I was joking with you, but that's what it is. So with the because right there I showed everybody this, but I'm like, I'm gonna let him really go into this. But I liked how you had the HR diagram. I don't know if I could be wrong, but were you actually demonstrating how those move off and on? Because they do a zigzag pattern.
Yeah, let me put the screen back on for you.
Because I loved seeing that, because I usually try to tell people like, hey, our sun's actually going to go over here, Aldebaran size, then it's actually going to return to it, and then it's going to go back. And this was awesome to see, like, but actually in a simulation like this.
Yeah. So are you seeing the diagram again?
Yep.
Okay, I'll press play. So right. So just like the stars move around in the sky, they also change colors and sizes. And this is one way that we, put that onto a diagram and visualize it. But as usual, when you look at one cluster with real observations, you see one time snapshot. And right now I'm showing what you can get on a computer model, where you see all the time snapshots and you can pull it together into a movie and watch the evolution. But yes, so stars are born on that kind of line that you saw, which is called the main sequence. And on the main sequence, they're very stable, burning hydrogen, fusing hydrogen in their core, and that gives them the energy that they need to keep themselves looking the way they are. But then once that fuel runs out, processes start happening more quickly, different burning locations, different energy sources, and the stars get bigger, and eventually they die. Some of them explode in supernovae. This is just a funny way that I ended it.
Yeah, no, I think that's really cool. And what you see there is the reason why you're seeing so much activity on the top, and please correct me if I'm wrong, but is because those stars that are born, upper with higher mass, bigger stars, especially, like blue massive stars, they're going to go through their resources quicker. So that's why you see a lot of movement up there in millions of years versus like a star like our own. We would be moving off of that at a much slower rate because our star is not as massive. And that's what I really liked about that, is because it showed dynamically how that would work with, massive stars versus lower mass stars.
Yeah.
So, Aaron, have a question. So you said that was the Pleiades star cluster that you were like some cluster approximately like the Pleiades?
That's right. Yeah.
What is the difference in like how you approach modeling an open cluster like the Pleiades versus a globular cluster?
That's a good question. So we do if there's few enough stars, we can model the exact position that they are in the cluster over time. And that's a direct calculation of the force of gravity, essentially, between any star and all of the other stars. And that gives you, the most accurate picture of how the cluster will change with time. But it's very computationally intensive. So if you want to do that for star clusters that might have hundreds of thousands or millions of stars, you can do a different way where it's more of a statistical representation. And you basically know the orbits of every star around the cluster over time. And that gives you a very good understanding of how the cluster evolves. It's just a different tool that you can use, and you can push to larger and larger numbers like the globular clusters. Though with some of the advances in software and hardware, these direct n-body calculations, the ones that we generally run for the lower number of stars clusters like the Pleiades, those are approaching the sizes of globular clusters. So you might be able to do millions of stars in a realistic globular cluster soon. People are working on that now.
Yeah, I had someone in my chat just say, yeah, the in-body problem. Yeah.
Mm-hmm.
And that's exactly, yeah, these are what those simulations are. That's a lot of what is on his site. You'll see that. And so can you talk about the differences between globular and, because I have talked about it, but it's good hearing it from you, and then between globular and open, and also gravitationally how those interact, because obviously different things are happening, right?
Yeah, so the globular clusters are, so there's a few differences. Some of the key differences are that in our galaxy, globular clusters are all old. So they're essentially, as old as the universe, between 10 and 12 billion years for most of them in our galaxy. And open clusters are a whole range of ages. So when I talk about an age of a star cluster, that means that pretty much all the stars in there were born that many years ago. So the way that we understand how stars form is many of them form in clusters. Some of them form in very large clusters like globular clusters. And in our galaxy, those stars formed 10 to 12 billion years ago. And there are a few hundred globular clusters in our galaxy. They're kind of distributed all around, centered on the center of our galaxy in kind of a spherical distribution. And in contrast, the open clusters have less stars. They tend to be younger, and they tend to be located in the disk of our galaxy.
Yeah, I'm showing everybody right now M3, Messier 3, which is a globular on my screen. I don't know if you can see it, but just so everybody can kind of get an idea, this is a globular, and I showed them right before we started the difference of this one versus this one, which is an open cluster, which is NGC 188. That's pretty interesting. With these though, and I don't know, I heard recently that it's possible you can get within globular clusters, you can get 3 different generations of stars. Is that, I don't know if that's even true, because it kind of blew my mind, because I've always thought that they were all like maybe 1 generation of stars, not 3.
Right. So that is the traditional view for a long time, was that all of these star clusters, all the stars in a given star cluster were born at the same time out of a cloud of gas that had a certain composition. So then all the stars today should be the same age, and they should have the same composition. And then when you plot them up on a color magnitude diagram or an HR diagram, they should form a very nice tight sequence, like I showed you from that computer model. But with better and better observations, particularly in the globular clusters, it's beginning to look like maybe all of them have multiple generations of stars, or stars with multiple different abundances of elements, so that you don't have just one sequence on that diagram. You have multiple sequences that kind of overlap and blur together. And this is one of the currently unsolved problems or questions in astronomy that people want to know, how do these multiple generations happen? And of course, there's plenty of different theories, and there's plenty of people who argue one way or the other. But the main difficulty is that stars form out of gas, and that's okay when the stars are just forming out of their kind of birth cloud. They're all forming at the same time out of this gas, and then they eat up some gas and become stars. Eventually every star has a wind. Our sun also has a wind, but particles streaming off of the stars push against the gas and start clearing it out. And then some supernovae go off. The most massive stars explode, and that really clears out the gas. So
Like a shockwave
at
type
some point
thing.
you need to get more gas so that you can have the stars form out of new gas. And the question is really, how does that get in there?
And is this where blue stragglers would come in?
So blue stragglers are actually a different phenomenon, actually, from what we were just discussing, we think, at least. So what we were just discussing is you can have multiple generations of stars that just form normally out of gas, the same way that every star does, but just forming at a different time in the same star cluster. Blue stragglers are another type of star that can form within star clusters and within the field of our galaxy, and looks different from the rest of the stars. And you can think of them as being younger than the rest of the stars because of where they live on that type of HR diagram. What we believe that blue stragglers are is the product of either two stars colliding with each other and combining to become one new star, or two stars that are very close together and one is kind of eating mass off of the other one, and then it's able to kind of gain more fuel and live a little bit longer. Or two stars that are just in a close binary configuration where they're orbiting about each other, but they get a little bit too close and then they merge and coalesce and become one star. And so all of those processes are able to somehow allow a star to maybe get more fuel in its center, more hydrogen in its center, and allow it to live a little bit longer on what's called the main sequence, on that branch of that diagram where they're happily fusing hydrogen in their core before things go crazy and they become giants and then die.
So I have a question. Do we know much about the origins of globular clusters? Because they seem kind of mysterious in terms of, like, they didn't form, they formed, like, to some extent even before the galaxy, right?
Yes.
Well, I mean, you fill in the blanks.
Yeah. Yeah, I mean, it's actually back when many years ago, when we didn't really know the ages of the clusters and we didn't really know the age of the universe, there was some tension between different measurements of the age of the universe and different measurements of the ages of the globular clusters in our galaxy. And in some cases, the globular clusters seemed older than what people said was the age of the universe, which obviously can't be right. But that has since been resolved, but it's still the case that globular clusters in our galaxy are nearly the age of the universe. And we don't see globular clusters forming in our galaxy right now. We see star clusters like our globular clusters forming in other galaxies. But the origin of the globular clusters in our galaxy is not, I wouldn't say that it's known. It's possible that they are kind of remnants of other galaxies or pieces of other galaxies as galaxies have collided with our Milky Way and been combined with our Milky Way. And these are the leftover, could be the leftover kind of central parts of those galaxies, or they could have formed in those galaxies and just kind of accreted onto ours. But that, as with many things in astronomy, that's not settled. So it's an interesting question.
Are there black holes?
Are there black holes in the globular clusters? Well, I will say yes. That's actually work. People at Northwestern do a lot of work in this, trying to figure out if there are black holes in globular clusters. Some of the models that the people here run are trying to understand how many black holes there might be in globular clusters. There are observations that suggest that there are black holes in globular clusters, but black holes are not easy to discover, right? I mean, they don't emit light. That's what makes them black holes. You only see them when they're interacting with something else. So they're interacting with another star and matter is falling onto the black hole. You may see some hot spot around the black hole and be able to infer that there's a black hole there. Or if there are two black holes and they spiral into each other, they might emit gravitational waves. You might detect that through an instrument like LIGO. And people here are trying to understand if, for instance, those gravitational wave signals from black holes might be from black holes that formed in globular clusters or elsewhere.
What about open clusters?
Yeah, that's so a lot of people are focusing on the black holes in globular clusters. I and some of my students have been looking into black holes in open clusters through more computer models. And that, model with that video that I showed you of the Pleiades had a whole bunch of black holes that formed and then were kicked out, and a few of them stayed around. We don't know if the Pleiades actually has black holes, but it might.
Like one of the, I guess you could say, globular clusters. Would you say Omega Centauri is a globular?
Right. So Omega Centauri is one of the most interesting clusters in our galaxy. It's different from most other globular clusters in a few ways. And one way is that it has quite a few different generations. So I don't remember what the count is at now, but many more, I think, than any other globular cluster that we've seen. And a lot of people think that Omega Centauri is really the remnant of a dwarf galaxy that was accreted onto ours, and that's why it looks so different, or maybe gives us a clue of where the other globular clusters come from. In terms of black holes in there, you know, we don't really know how many there could be. And one of the best ways that we could find out is through running computer models to see, you know, how do our computer models with lots of black holes match the real star clusters themselves, where you can see the luminous stars like our sun, but you can't see the black holes.
And watching those orbits, right? Just watching the stars' orbits and how they're manipulated, right?
Yeah,
Maybe?
so it turns out that if you have a lot of black holes in your star cluster, it kind of puffs up the cluster in general. So you wouldn't get a very dense core of luminous stars. Instead, you would have a dense core of black holes, and they kind of, you know, move around themselves and kick out the luminous stars. So when you would look at a real globular cluster that has lots of black holes, it would not be as dense in the center. It would not appear as dense in the center when you're looking at the visible light, as a cluster would be if it didn't have very many black holes. And so that's one of the ways that people here at Northwestern are trying to distinguish between clusters who have a lot of black holes potentially and those that don't, in comparison to the models that are run here.
And what part of the wavelength do they look? Is it infrared or X-ray to observe that?
Well, yeah. So if you're trying to do a test like I was just saying, where you're trying to see how kind of dense the stars are toward the center of the cluster, you want to look in, you could look in infrared or visible light, and you want to be using a telescope that is probably in space, because you need very high resolution, very able to see very small distances, differentiate stars that are very close together in the sky, so that they don't all just blend together and become one kind of bright central thing. So people do that, and but people also are looking for actually signals from black holes, and people will look, for instance, in the radio or X-ray,
Mm-hmm.
and or gravitational waves.
That's really cool. So what's one of the things, because I know, again, like you said, you study how exoplanets could exist in these things. What do you study? Can you go in a little bit more of that, like how planets would behave in these open or globular cluster systems?
Yeah, so that I find that to be a very kind of interesting question, kind of like a romantic question, but it's actually a very hard one to answer very well. So there are a few lines of evidence that suggest that our sun was born in a star cluster that might have had a few thousand stars, maybe similar to the Pleiades, for instance, that movie that I showed. And over time, our star found its way, wandered out of the star cluster. The star cluster probably dissolved, which is, the Pleiades is on its way to dissolving as well. And now our star is just on its own with its planets. But if our star, and if most stars for that matter, are born in an environment where there are more stars nearby, that's more dynamically active, and stars can come very close to each other, the question that I want to understand is, how often do stars get close enough together that they could disrupt planets that are orbiting around another star? So how often would they disrupt our solar system if you put our solar system into a star cluster? And so part of this is, these are questions that a lot of people are interested in. And some people are attacking this through observations, for instance, using the Kepler satellite, which has been looking at various star clusters, and also the new TESS satellite, which will be launched soon, and will also look at star clusters, trying to understand, how many stars have planets that are in star clusters. And then I am trying, and my collaborators are trying to answer this through computer models. So we're trying to run computer models with stars, like you saw in that movie, but also with planets around maybe every star. and maybe like our solar system, and trying to see how often they get disrupted.
And are binary stars very common in these cluster types, or are they more common in one cluster than another type of cluster?
Yeah, binary stars are another topic that I've studied, and actually dating all the way back to my thesis. Yeah, so binary stars are, most stars like our sun actually have a stellar companion. And our sun might be a little strange because it doesn't, right? So if you actually were to look out, for instance, if you look out in the sky and you see stars that look like our sun, they're so far away that you probably, no matter, if there were two or three of them orbiting each other, you would see one point of light because they're so far away. But even though you might see two separate points of light over in different spots of the sky, the statistically speaking, one of those is actually a binary star. So basically half of the stars, like our sun, have another companion. And it looks like that fraction changes with how massive the star is. So more massive stars tend to have more frequently have companions than our sun. And we put those into our model, and we try to see how those binary star populations change with time. And one of the main things that happens is if, for instance, you put a binary system into a star cluster, two stars, orbiting each other, in the middle of a star cluster where there's a whole bunch of stars flying around, the widest binaries get disrupted by other stars that essentially zoom right by them and, intersect with their orbits. And those type of encounters that you saw in that movie that I showed, those can change the binary star population and also change the planet population. And so I try to understand how it will change those populations.
So did you say that the more massive stars tend to form in binaries? Like they form in binaries more often than the less massive stars?
That's what it seems like. So it could be that every massive star forms with another star in a binary, or almost every massive star forms in a binary, which is unlike our sun. Meaning our sun, it's basically 1 out of every 2 times that you form a star like our sun, you form 2 stars.
So having like the binary M dwarfs, that those would be even more valuable because, one, we don't really understand the lowest mass stars, like there's the mass radius relationship that you get at the lowest mass. And in order to do that, you have to be able to study these systems, and they're even more rare than you would get otherwise. Is that a fair statement?
Yes, that is true. Yeah. So right. So going in the other direction of mass, the M dwarfs, which are the lower mass stars, have a much lower frequency of binaries. So yeah, so they're harder to find those in binaries, and of course they're fainter. So
harder to find all around.
That's right.
And so, what I'm curious about though is like talking about generational, stars. There's going to be, like you said, there's different compositions for some of these stars that you've looked at. And I don't really know a lot about really how that works. So I guess what I'm saying is if you have a older galaxy, older cluster, those stars might have a different composition than, say, an open cluster with a variety of stars that some might be younger. Can you talk a little bit more about what you mean by difference in composition?
Sure. So if you think of a very simple model of the galaxy and of the universe, for that matter, you start out with mostly hydrogen. It's a very simple element, and it's very plentiful in the universe, and was one of the first ones that was formed. And the only way that you get the heavier elements, like the things that make up you and me, and all the things that that go into this computer that we're talking on, the only way that you're getting those is through fusion or different processes that happen in stars. So the first generations of stars formed were all or the vast majority of it was hydrogen. And through their lives in the cores of those stars, they fuse hydrogen to helium, and then into carbon, nitrogen, oxygen, and up to iron. And that is kind of the process that happens inside very massive stars, and it's that's where we get our iron, essentially. And so after that first generation of stars, they form, some of them explode in supernovae, kind of polluting the rest of the gas in the galaxy with those heavier elements. Some of that can get swept up into a new cloud of gas that, might be mostly hydrogen, but now has some of the heavier elements in there. That forms into new stars that might form into the next generation of star cluster. And so now these stars have a different composition, and they're a little younger than those older stars that were in that first cluster. And that can kind of progress on and on as you continue polluting the gas from previous generations of stars and making new generations of stars that have more and more of these heavier elements in them.
And that would also impact the kind of planets that would form around those stars with the heavier elements, right? Maybe?
Sure. I mean, of course, if you want to make a planet like Earth, you need more than just hydrogen.
Right.
So you need some environment that has, all of the different elements that make up Earth, that make rock. And that, there's more of that in an environment that has been polluted by these stars.
Yeah, unlike hot Jupiters, which are mostly hydrogen and helium, right?
Yeah, exactly. Sorry about that.
It's okay. Yeah, so that's kind of how that would be different. That's yeah, I know a few people have asked about me talking about like carbon stars and things like that. And I don't really know enough about that to just wing it. I'd have to do some research myself. But as far as what has been your most interesting thing that you've studied that you like, that's most interesting to you about what you're doing, and or maybe the most mind-blowing? That's what I like to say to everybody here.
The most mind-blowing.
Yes.
Well, I mean, even just going back to the work that I was doing for my thesis, I mean, realizing that stars can collide with each other and can get close enough that they interact in a way that, one basically swallows up another. That's pretty cool, and being able to actually look up and find stars in the sky that we think went through that, that is really cool. And, I still find that very interesting, even though I don't necessarily study that quite as often. I'm looking at, I still do study that quite a bit. But I'm now even more fascinated by, planets around stars. And I'm having a good time doing different visualizations, like that movie that I showed you, and kind of communicating all this with museum goers at the Adler Planetarium, for instance.
So, question for you. What are some of the unusual issues that you run into when you're simulating these different things? So I'm thinking, like, for example, the time step things. Can you explain
Sure.
some of the?
Yeah, sure. So one of the main challenges to making a model that has a whole bunch of stars, like a star cluster, and also a whole bunch of planets orbiting those stars, is this issue that you were just saying, the time scales. So stars, orbit around the cluster, and they change their sizes and colors on timescales of like millions of years. And so if you just want to track the stars, that is fine. So you can, run your model so that it calculates where the star will be a million years from now, for instance, or maybe a little less than that. But you don't need to have very high resolution in time to see that, which means that you don't need to, the computer doesn't need to do quite as much work. But if you want to track the orbit of our solar system, for instance, or the Earth around the sun, then you need timescales that are of the order of a year, 1 year, right, and less, because you can't just have 1 year. You need to let that, the gravity calculation happen multiple times around the orbit, so that you know where it is, so that you can keep track of where its next step will be. And so you have 1 year versus millions of years, and you want to run this maybe for billions of years, because maybe the star cluster is billions of years old. And that becomes very challenging computationally. So there are different schemes that we try to figure out on how to handle that. And that is something that's been solved. So you can think it's a kind of a similar problem for binary stars. Two stars might be orbiting each other on a period of a year. And if you just have two stars, you don't actually need to calculate the force of gravity on them. You can calculate how the orbit changes with time. And that can be done, and that allows us to do these type of models that I show with binary stars and the motion of the stars through the galaxy. But once you get to, and so you could do that with a star and a single planet in the same way. Many stars with only one planet, you could do in the same way. But once you get to 3 or really 4 or 5 planets in a system, you really do need to do the calculation, the full calculation of gravity. And again, that's a very short time step that you need to do it accurately. And then you're asking a lot of a computer if you want to have thousands of these systems all calculate at the same time, and you want to do this for billions of time steps. And so some of the ways that we try to solve this is through large computers, where we can send one individual planet system to be calculated on its own processor, on its own time step. And then when we need to know about that, when it comes close to another star, we can bring it together on another processor, for instance, to figure that encounter out. So you can do a lot of it in parallel, is basically what I'm trying to say. And that's a complex problem to write a computer code to do that.
Yeah. Yeah. So, hey guys, coding happens in astronomy. And my question that I'm curious about is what happens to globular open clusters? And then we can start doing questions after that. But yeah, what happens to them?
A lot of the open clusters dissolve. So a lot of stars that form in a group of stars, if it's like 100 stars or 1,000 stars, that might live as a family, as a star cluster for, a few 100 million years. And then it starts to spread out and just become part of the galaxy. The field of our galaxy is what we call it, and which is probably what happened to our sun. And the more and more stars that you form with, the larger the gravitational potential, the more tightly bound they are relative to the pull of the galaxy, and they can survive as a cluster for a longer period of time. So the globular clusters, which are have much more stars, many more stars, are still around as clusters, but they are constantly, losing stars, but maybe not as rapidly as some of the open clusters because they don't come quite as close to the center of the galaxy, and they don't pass through the disk as often.
Awesome. Well, I think if we have questions from anybody, or if Dr. Stefan has any ones that he was kind of holding off on too, I think I asked my moderators if there were any. I know I saw a few come in. Or Dr. Stefan, did you catch any yourself?
There were a few. One of them was, what role would the James Webb Space Telescope play in? Or let me ask it in kind of a broader context, and that is, how do you match your computer simulations to observations? What are the things that you pull out of your computer simulations that match to observations? And how will new observations improve with new instruments that can help inform the theory side?
Yeah, that's a good question. There are quite a few different ways that we try to compare the simulations to the observations. So one is, for instance, we're talking about how concentrated these clusters are, how tightly packed the stars are toward the center. You can parameterize that as a radius from the center where either half of the stars are within or half of the light is within. And you can do that for real observations as it's projected on the sky. And you can also do that in the simulations. And that's one way that you can compare. You can compare the HR diagram, or that color magnitude diagram. So the temperatures and the luminosities of the stars, you can compare that to the simulations. And you can compare stuff that I have done more of, is you can compare the binary star populations. So you can compare how many stars are in binaries and what their typical orbital periods are, what their year is, different parameters of their orbits. And those are observations that you can, or data that you can get from observations through radial velocities. So time series measurements of the velocity that the stars are moving toward and away from us. When you have two stars that they're orbiting in a binary, to depending on how they're oriented, if they're oriented in the right way, their star is going to wobble toward and away from us. And if you watch it with time, over time, you can see that wobble and figure out some of the parameters of that binary. And another way that you can figure out for binaries is looking for brightness variations. So in the same way that you search for planets, you've probably heard a lot about transiting planets. You can have eclipsing binaries, which is one star that goes in front of another, and the light changes when that happens. Actually, both of those techniques are used to search for planets. They work the same way. You just need to be more sensitive to get planets. And so all of that are different avenues for comparing against our simulations. If you get even more kind of detailed measurements of the composition of the stars, you can compare that against different, more detailed simulations to try to see if we understand really what's happening. So really, the more it is always the case that the more observations you get, the more we tend to understand. And then also the more questions we have and the more things that we realize we need to kind of improve in our theoretical understanding in our models. So they really work hand in hand. It's very important to have both to understand what we should be looking for and how we should be looking for it, and then understand how we should improve the physics in our models.
Yeah, there's actually a really good question that just came up. It said, is NGC 188 as an open cluster just as special as Omega Centauri as a globular? It looked so round and massive.
It has a special place in my heart.
Yeah.
It's special in its own way. So NGC 188 is, for the work that I do, one of the most important star clusters, partly because, like I said, it's actually in a region of the sky where you can observe it almost every night when it's clear outside from the northern hemisphere, which means that you can basically, you can have exquisite kind of time series measurements, and that is important for understanding binary stars, for instance. And there are just a handful of star clusters that have been studied at that level of detail. NGC 188 is closer to us than Omega Centauri, and therefore the stars are a little bit brighter, which makes it easier to observe. It's closer to us and not as dense, which means the stars are separated a bit more than the stars in Omega Centauri. So we can really observe every star that is like our sun, for instance, in NGC 188. There's no issue with stars being too close to each other. But that is not true for Omega Centauri. Stars get too close together, and from the ground, it becomes very hard to do that type of observations that we can do for NGC 188. So each of them, hold a different reason why they're important. Omega Centauri offers a different environment, so stars move around more quickly and are much closer together, so it's more dynamically active. So it's interesting from a dynamic standpoint.
Awesome.
So, we've got one question that is, what is the relationship between the properties of star clusters and the environments from which they form?
Well, so one of the properties, of course, is the composition of the star. So if they form out of a cloud of gas that has been polluted by a lot of different with a lot of heavier elements, the stars themselves will have a different composition. And some of the things that are interesting and at kind of the forefront of these type of models and also observations is really trying to dig into that early stage of formation and the dynamics that happen there, where you look at a lot of these star clusters and a lot of the models, and even the model that I showed, it looks like things are very spherically symmetric. But when they formed, they may have formed in filaments, or they may have formed in little chunks that were more dense that then fell into each other. And at that point, the stars were much closer together. And, they could have come very close to each other and disrupted binary stars or planets. And then it relaxed a little bit and looks kind of the spherical ball that we see today. But a lot of what is very interesting in terms of the dynamics may have happened very early on. And that's something that we're studying as well, yeah.
What about another one that we got from the chat is what of these where do we look to find these star clusters? If you were just had a pair of binoculars or a small telescope or something like that,
Yeah.
what can you expect to see when you?
Yeah. So, well, you want to look online at, there's, a few different lists, the Messier list, M some number, or NGC some number, and look for, those are cataloged. They're not all star clusters, but those are cataloged objects, extended objects. And so binoculars and really small backyard telescopes can be really nice for globular clusters and open clusters. You can expect for, globular clusters, it's going to look like a fuzzy ball. And maybe around the edges, you'll see individual stars. But when you look with your eyes, it will look like just one point of light. And then you'll put a telescope on and you'll realize that it's actually hundreds of thousands and maybe millions of stars.
Yeah, and that happened with Omega Centauri. They thought for the longest time that it was just a star.
Yep. Exactly.
And I'm sorry, is there anything you want to add with that?
Well, I would say, I think these are some of the more exciting things to look at, the globular clusters and the open clusters when you get binoculars and telescope.
Yeah, and someone asked a good question. In all seriousness, can Dr. Geller name drop the programs they use, or are they proprietary?
No, they're not proprietary at all. Actually, the one that I use to calculate the positions of those stars in that movie was called N-body 6, the number 6, and the word N-body. And you can Google that. That is Sfera Arseth is a astronomer who has basically devoted his entire career to making computer code that can run these star cluster models efficiently, and you can download it from his website and run it yourself.
Wow, that's actually really nice. There you go.
Yep.
And is it possible that all stars are born in clusters?
Yes, I think it is. It's possible. It may not be every single star, and it also, now you're getting into some type of astronomy jargon of whether you want to call it a cluster or an association or a group of stars. But I think it's probably true that nearly every star is born with some other stars nearby. And whether or not they end up coming out as a group that we would call a star cluster, I don't think they all come out that way. But it's most likely that most stars form with many stars around them.
Awesome. And someone says,
quick question: what about the software that you use to make your visualizations?
Yeah, so the one that I just showed you there is with software called Uniview, and that's developed by a company called SCISS, SCISS, and that and so there's a credit at the end of the movie also rendered in with Uniview. That is software that you have to pay for. But I've been doing a lot more actually with OpenGL and WebGL, and actually Uniview it has a lot in OpenGL, so a lot of what is in that visualization was basically written in OpenGL. So for those of you that are looking to do something on your own, that's a great place to start. There's also other open source type of visualization tools that I have used. One is called PartyView. Party with an I, like particle, PartyView. So that is something that you can download for free and run. You just have to put your files in the right format and you can create some things. And I actually think I have a movie on my website that was rendered from PartyView. So that's an interesting one to be able to use, just download and use.
Do you know which movie that would be? So I can, in the visualization.
Yeah, it's actually just another version of the one that I showed. I'll pull up my page and tell you what it is. So you would, scrolling down, the evolution of a Pleiades-like star cluster. Yeah, so it's just below the one that I showed in PartyView.
Oh, okay.
I have done many generations of this different movie with different tools just to try to see it in different ways.
And guys,
I think it's a different simulation out of the same family of models.
Yeah, I just linked where all the visualizations, wow, words, where they all are on on there. So you guys, we're going to look at some of those, but I don't want to keep him. He has been here as long as we have about 5 minutes, but
Yep.
I just want to make sure that if anybody has any questions that I haven't missed. Dr. Stefan, did you see any that I might have missed, or?
I think we got most of them.
Yeah.
So I think that went really well. I mean, I really like this stuff. It's not the dynamics, that I studied when I was at Northwestern, but it's kind of the more mysterious stuff. I mean, in my mind, whatever I'm studying, I don't know, there's always greener pastures. And I find it's, especially with globular clusters, that they're pretty mysterious objects that we don't really know their origins, and we don't know. I guess one thing that I was thinking about as you were talking is that they may, if you form a galaxy out of small blobs that aren't dark matter dominated, because towards the center of the galaxy, it's not dark matter dominated. It's actually dominated by regular matter. You briefly mentioned this. Do you think that that's that the globular clusters may be leftover proto-galactic cores?
Yeah, I think that's a really interesting possibility. And if you look at some of the models of like cosmological models where they have the formation of a Milky Way type galaxy, they predict a lot of these smaller galaxies falling into the Milky Way as part of how the Milky Way would form. And yeah, that's kind of a natural outcome that might, fall out of a simulation like that, and be where the globular clusters come from.
Yeah, someone just said, is it possible that our star was a binary star? And I think isn't that where that whole Nibiru thing comes from? Or something like that?
Exactly. Wasn't the world supposed to end very recently?
Yeah, I think like last Saturday or the Saturday before, I don't remember. But yeah, I mean, it's something, I think, you might agree, anything's kind of possible, but finding that would be extremely difficult, right?
Yeah, well, the most exciting thing that's happened in our solar system recently has been the discovery of possible 9th planet, Planet 9. Mm-hmm. And, a star would be a little brighter than that, mm-hmm. I think, unless it's very far away. We haven't detected Planet 9 through a telescope yet. And we haven't detected another star either. But yeah, theories are out there that there could be another star, and people are looking for it.
Mm-hmm. Yep. Nibiru or Nemesis. I don't know. Those are both horrible names for celestial objects, and shame on whoever would name them either of those. And they probably wouldn't be named that in time. So, but I do want to, someone says it was Pluto all along. I do want to thank you, and I don't want to take up any more of your time. Thank you so much for coming on here, and everybody really enjoyed it. I can already tell people are like, thank you, Dr. Geller. So, yeah, so thank you so much for your time. And Dr. Stefan, do you have any closing anything?
I can stick around for a few minutes, but then I need to go on to my next thing as well. But thanks, Aaron. I appreciate your time.
Yeah, thanks for having me. It was fun.
I hope you enjoy the next few months of weather that's coming your way.
Yeah, yeah, it's gonna get a little colder. It's nice here now, though. Mm-hmm. I'm enjoying it while it lasts.
Awesome. Well, thank you guys so much. And Dr. Stefan, did you say you wanted to stay on with me?
I can if you'd like me to. Otherwise, I can just lurk in the chat.
Yeah, I think I'm gonna get up and stretch and stuff. But
okay.
Yeah. So thank you guys so much.
Thanks. You.
All right. Bye-bye, guys. There you guys go. That was awesome. How'd you guys like that? I know that a lot of people think that that's really dense material, and it kind of is. It not. We can talk about it a little bit more, but actually he's yeah. I like him. He's very good at talking about this kind of stuff. And I don't know if you guys got tripped up at all or anything, but we can kind of go over that right now. I do have this open cluster, the one that he did a lot of work with. Right here, right now. This is NGC 188. We should do that more often. We do. And you know, and if there's something that really cool that comes up with